So like Fabian's talk, this will be about a theoretical result, a security proof for continuous variable QKD. For a slightly different protocol, where we use coherent states instead of squeeze states. So the advantage of talking last in the session is that I don't have to introduce all the formalism about continuous variable QKD, so I will be very fast about this. Just continuous variable QKD refers really to the detection scheme. Okay, you use homodyne or heterodyne detection, but there are different kind of protocols. They can use squeeze states, as in Fabian's talk, or they can use coherent states. And of course, from a practical point of view, coherent states are much more convenient because they're really easy to prepare in the lab. Okay, so in terms of experiments, there have been very nice results with demonstration of continuous variable QKD with coherent states. We can achieve kind of large distances. We have systems which are very stable over several months. There is even a commercial product sold by SecureNet. Okay, so this is very nice, but what about the security of this kind of protocols? Okay, so again, thanks to Renato's very nice talk yesterday, I don't have to explain what is composable security, but just to remind you, it's just basically getting an epsilon. Okay, you want to quantify the security and you want to compute an epsilon to say what is the security of your key. And basically, the epsilon is composed of several parts. So you want your protocol to be correct. So you want Alice and Bob's keys to be identical, and you can do that up to some epsilon probability of error. You want your key to be secret, of course. What does that mean? It means that basically the joint state of the key and Eve should be a product state, okay? And the key should be uniformly random, okay? And you see that your protocol is epsilon secure if it is both correct and secret, right? And you also want, so one other parameter that you want is this robustness, okay? You want that if there is no active eavesdropper, you want, so in general conditions, you have like your passive optical fiber, you want that the protocol will produce some key with high probability. Okay, so this is what you want. So how do you do that? So basically, as far as I know, there are like two different approaches to prove composable security of QKD in general, and also for continuous variable QKD. So the first approach is this entropic uncertainty principle that Fabian mentioned before. So in the case of discrete variable protocols, such as BB84, this entropic uncertainty principle is really the best tool that we have. Okay? This is the technique that will give you the tightest key rate. Okay? And this has been successfully ported to the continuous variable paradigm by Fabian in this PRL 2 years ago, and now you can even work with reverse reconciliation, as Fabian explained, and there are even experiments doing this. So this is all very nice, but there are some caveats. So one of them is that this only works for protocols using squeeze states. Okay, so this is a bit annoying because you would like to have security even for protocols with coherent states. So this doesn't work for this. And another caveat is that we have this discrepancy between the key rate that you obtain with this method and what we believe to be the tight key rate, which is the one that would be given by Gaussian attacks. Okay? So this is the first kind of technique to prove composable security. The second approach is really a two-step approach. So the first step, you prove that it's enough to consider collective attacks. Okay, so you have this reduction. You can show that if your protocol is epsilon secure against collective attacks, then it will be epsilon prime secure against general attacks, with epsilon prime larger than epsilon. Okay, and once you have this, all is left to do is really to prove security against collective attacks, which is much easier in general. So this first step has been done for continuous variables. So there are like so far, there are two techniques to do that. There is this definity theorem by Renato and Ignacio Sirac, and there's also post-selection technique. But so we have two techniques to do that, but these techniques are not optimal, and there is really like a loss in this reduction. The epsilon parameter that you get is really much worse for general attacks than collective attacks. But I'll come back to that later. But anyway, so we have this step in theory is done, and we are left with the second step, which is proving composable security against collective attacks. So far we don't have that. What we have a couple of security proofs from 2006, which are for attacks, for collective attacks, but they always assume that the covariance matrix is given. Okay, and so you have no parameter estimation in these proofs. So you assume that basically you know the covariance matrix of your state, and if it's the case, then you can prove security. But this is not. This does not give you composable security. Okay, so in this talk, I will prove the composable security of continuous variable QKD against collective attacks. And to do that, the main new tool is a parameter estimation procedure, which is assumption-free. So you don't need any assumption about your state. Okay. So first, let me describe the protocol to you. So I will describe the entanglement-based version of the protocol, and I will use reverse reconciliation. Okay, so there are like a number of steps. So some of them are standard, some are a little bit new. So the first step is Alice prepares a bunch of 2-mode squeeze states. Okay, so 2n of them. So in the prepare and measure version, she would just prepare coherent states. So it's very easy to do. Okay, so this is the preparation. Then Alice distributes one register to Bob. So for each 2-mode squeeze state, she will send register A prime to Bob. And because we consider only collective attacks, the quantum channel is IID, and the state that Alice and Bob share after the distribution has this tensor product structure. Okay. Then they proceed with measurements, so they measure their states. So they have, both Alice and Bob have 2n modes, and they will measure their modes with heterodyne detection. So heterodyne detection gives you 2 outcomes for each mode. So Alice and Bob, they end up with 4n real variables, each of them. So they have both one big 4n vector. So Alice has the vector x. This is our measurement results, and Bob has y. Okay. Then, because we use this reverse reconciliation, Bob, so the secret key will be extracted from Bob row key, which is y. So he needs to discretize his key, so y. So you discretize each variable with d bits, and you end up with a bit string u. Okay, so this will be the row key. Then we proceed with error correction. So this is a bit somewhat new. In general, in QKD protocols, you always do parameter estimation and then only do error correction. Here it's kind of crucial that you do the other way around. So you first do error correction, and then you will do parameter estimation. So to do this error correction, it's quite standard. Bob will send the syndrome of his string u to Alice for a given error correcting code. And Alice will decode will decode this code, basically, and she will output a guess for u. Okay, and then Alice and Bob, they can just, to be sure that they have the same, that this error correction worked, they can just compute a small hash of both their strings, and they compare them. And if they are equal, they continue the protocol. If they differ, they abort. Okay. So now, once this step is done, Bob knows y and u, and Alice knows her guess for u. But in general, it will be equal to u. So it means that Alice knows x and u. Okay, then you have the parameter estimation phase. So basically, for continuous variable protocols, what you need to do is to estimate the covariance matrix. And it turns out that a good proxy for this covariance matrix is basically these three variables. So the square norm of the vector x, the square norm of the vector y, and the dot product between both x and y. Okay, so it's very easy for Alice to compute these three numbers. And then you have this parameter estimation test that is something like this. So for this test, you have three parameters, which are these three numbers, sigma A max, sigma B max, and sigma C min. So these are basically the variance for Alice, the variance for Bob, and the correlations between Alice and Bob. And this parameter estimation test kind of checks that the correlations are high enough and that the respective variances for Alice and Bob are not too large. These gamma A, gamma B, gamma C, they are just functions of these three numbers that Alice can compute, and she can check whether this test passes or not. If the test doesn't pass, they abort the protocol. If it passes, they proceed with privacy amplification, so they apply a random universal hash function to their respective strings, and they obtain two secret strings of size L. Okay, so this is the protocol. And the main result is that this protocol is epsilon secure against collective attacks if a certain number of conditions are satisfied. So epsilon has to be like this, and if the key rate, if the key size, L, is less than this value. Okay, so this value, basically this HMLE U is just the empirical entropy of the string U that Bob has. This F of sigma A max, sigma B max, and sigma C min is basically the mutual information between Eve and Y computed for a Gaussian state with this covariance matrix. This is easy to compute. This leakage is how much information Bob needs to send to Alice during the error correction phase. And you have also these small terms. Okay, but what you need to somehow see from this slide is that asymptotically, this converges to the value that you get when you consider Gaussian attacks. Okay, so this is really like tight. And the new tool to get this bound is really a robust estimation procedure of the covariance matrix that doesn't make any assumption about the state. Okay, so just to plot the key rate as a function. So here I'm looking at what would be an epsilon secure key rate for epsilon to be 10 to the minus 20 against collective attacks. And I plot the expected secret key rate as a function of the block size. Okay, so the different curves correspond to different distances. So the first one is 1 kilometer, this is 10 kilometers, 50 kilometers, and 100 kilometers. So if you go to large block sizes, you can go to long distances. But if you want to go to 100 kilometers, you need a really large block size. Okay? And I believe that this is almost tight. So if you want to use quantum key distribution with coherent states, and you want to use this approach to prove security, you will need really this kind of size for your blocks if you want to achieve long distances. Okay, so in the remaining part of the talk, I will just try to explain a little bit what is the parameter estimation procedure that we use. So as I said, in order to compute the key rate, basically what you need to do, what Alice and Bob need to do is really to compute the covariance matrix of the state that they share. And to see that this is not so easy, I give you like a simplified problem, which is basically a classical variant of this problem, where you have just x, which is a random variable with an unknown probability distribution over R, such that you know that the distribution is centered and you have a fixed variance which is bounded. Okay? And what you want to do is just to somehow compute the variance or to get an estimation for this variance. And you can observe n IID realizations of this random variable. And somehow you want to find, say, an upper bound for the variance. You want to say that the probability that the variance is larger than something is very small. So can you do it? Because this is exactly what you need to do for estimating the coherence matrix of the state. And it turns out that just like that, it's not possible because you can, and the reason is that the variable x is a priori unbounded. Okay, so it could be very well be the case that your variable is very small, a large part of time, but very rarely it takes a very large value. And if it's the case, then if you just observe observations but not enough, you will always observe these guys, but you will never see this. And the variance can be arbitrarily large if this amplitude is large enough. So this is really a problem. And how do you solve this problem? So there are different solutions. So you can either assume that you have a Gaussian distribution, in which case you don't have this thing. But if you do that, you don't have composable security. So it's not good. And the other solution is to symmetrize the state. Okay, so what do I mean by that? First, maybe I will just say a few words about quantum tomography, because parameter estimation is really like a coarse-grained version of quantum tomography. You don't want to know the state precisely, but you want to know some parameters of the state, like its covariance matrix. So there is a very nice framework that was introduced by Matthias Christendel and Renato Renner 2 years ago to study quantum tomography. So what is that? So basically, if you have like a number of copies of a given state and you want to do the tomography of the state, what should you do? The idea is that you will first take all these guys, you will somehow symmetrize this global state, and then you will somehow divide your global state into two parts. So you will give the first part to someone who will do a measurement, and you give the remaining part to someone else, which will hold the state. And the goal is for the first person, the one who does the measurement. So he will do some measurements, and his task will be to guess some characteristics of this remaining state. Okay, so this is really what you want to do when you do quantum tomography, and this is what you want to do when you do QKD. Okay, so in general, for discrete variable QKD, or for discrete variable quantum tomography, this symmetrization is just a random permutation that you can apply. If you want to do continuous variable QKD, you will need a more complicated symmetrization. Basically, in the example that I had before, so imagine that you have this this problem where you want to compute the variance of this thing. So now you can imagine that you have a vector. You have x1, x2 up to xn. So this is your classical vector, and you want to compute the variance of these variables. So basically, you want to estimate the norm of this vector. So basically, what you will do is, so if most of the coordinates are very small, but one sometimes can be very large, it's not a good idea to just pick at random some coordinates and look at them. What you should really do is to first apply your random rotation to your vector. And when you do that, the coordinates with a large amplitude, they will somehow spread out on all the other coordinates. And when you will measure here, you will get a very tight estimate for the norm of your vector. And this is basically the same idea that you want to do with continuous variable QKD. So you want Alice and Bob to apply this kind of symmetrization, which is Alice and Bob will apply conjugate random networks of beam splitters and phase shift to their modes. And then they will measure, and then they will do estimation, parameter estimation. So ideally, what you would like them to do is for Alice and Bob to apply this conjugate random networks of beam splitters and phase shifts. This is this symmetrization part. So they get a new state, which is like which has been randomized, and then somehow they distribute their two n modes. So they give the first n modes to new parties A1 and B1. Okay, we'll measure these n modes. And the goal of these two parties, A1 and B1, will be to do parameter estimation of the remaining n modes. Okay, and you can do the other way around. You can have A2 and B2 measuring their modes and try to estimate the first n modes. So just picture as a picture what this gives. So you start with your state, which is IID in the collective attack scenario. You first symmetrize it, and then you give the first n modes to Alice 1 and the first n modes of Bob to B1. And these two guys, they will measure their respective modes and they will try to guess the covariance matrix of the remaining states. Okay? And at the same time, these two guys, they can also measure their modes and they will try to estimate the covariance matrix of A1, B1. And if you combine both estimates, you can get a lower bound for the key size. Okay, so this looks good, except that you really don't want to do that in practice. You really don't want to symmetrize your state. You don't want to have additional parties. And the very nice thing is that it turns out that Alice can efficiently simulate all this process, all this symmetrization and distribution to additional parties. And so this can be proven with two technical lemmas. So first, you can show that if you are A1 and B1, so they have access to their measurement results. So these are two vectors. And if they want to estimate the covariance matrix of A2, B2, basically what all they need to know is these three values. So the norm of x1, the norm of y1, and the scalar product between both vectors. And it turns out that Alice, in the usual protocol, she knows the norm of x, the norm of y, and the correlation between x and y. And you can prove that if she knows these three numbers, she can infer a confidence region for these three numbers. So basically, what you can do is you have Alice knowing this thing, these three numbers. She will infer a confidence region for these three numbers now. And now she can somehow simulate what Alice A1 and B1 would have guessed for the parameter estimation. Okay, so this is the main idea of the parameter estimation procedure. And just to conclude, so we give the first composable security proof of continuous variable QKD with coherent states. The main new tool is this parameter estimation procedure for covariance matrices, which doesn't assume anything about the state. A nice thing about this procedure is that almost all the raw key is used to distill the secret key, because you have both A1 and B1 guessing the covariance matrix of A2 and B2 and the other way around, so you don't lose anything. I think the bound is fairly tight against collective attacks. But I would say that the main open question is to really improve a lot the reduction from general to collective attacks. So right now we have two techniques to do that. We have the Definity theorem, or we have the post-selection technique, but both of them are way too bad to give any sensible secret key rate for reasonable values of the block size. Okay, so this needs to be worked out. So I believe that this can be improved, but this has to be done. And I just want to mention that there is probably other applications for this parameter estimation procedure, and one of them is just to quantify bipartite continuous variable entanglement without any assumptions. And with that, I thank you for your attention.
How is error correction performed before doing parameter estimation, or
Yeah, so it's a good question. Turns out that basically for error correction, you don't really need to have like a very good estimate of the quantum channel. It's good if you know basically roughly the signal-to-noise ratio of your data. And this you can always, you know the channel because in practice, you know the channel and you know what signal-to-noise ratio you can expect. So you can always use an error correcting code that will work for this SNR. And most of the time it will work. Sometimes it won't work, and if it doesn't work, just abort. But basically, you don't need a very good parameter estimation to choose your error correcting code.
Well, I have a quick question as well. Look into the block sizes, the data block sizes. This seem to me a bit relatively large when I compare them to the discrete variable case.
Yes.
And this is against collective attacks.
Yes.
And of course, you said that, of course, against coherent attacks will be worse, but maybe there is some room to improve there. Is there, do you see also some room to improve here? Because you mentioned also that they are quite tight.
Yeah, honestly, I don't think that this can be improved a lot. Really, the problem is that the main problem is to estimate this excess noise in general. And this excess noise is the difference between the variance of your state and the shot noise. So this is the difference between two variances, and it's very hard to estimate this quantity precisely. And because of this, you kind of need very large block sizes. And even a few years ago, we had a paper with Frédéric and Philippe Granger, where we looked at finite size effects when we assumed Gaussian, that we had a Gaussian state. And even for this, in this case, the numbers were not much better than this. So I think you cannot expect to have reasonable key size for small block lengths.
Thank you. Are there any other questions?
It may be also a question to the previous speaker, which is about this discrepancy you spoke about with the entropic key rate. So both of your talks are about reverse reconciliation now. Mm-hmm. If I understand correctly, the entropic key rate is smaller, so it suggests that the entropic rate is not tight, or what is your comment on that?
Yeah, I think this is the case. The bound that Fabian has is not tight, so it doesn't give you the asymptotic key rate that you expect for a Gaussian attack. So,
is there any possible explanation for that, or?
Well, it's just that this entropic uncertainty principle is not tight, probably. I mean, in this, yeah, I don't know. Maybe we can. Yeah, or maybe please, or offline.
Okay, we'll discuss that later.